presentation down there.
Cool, I can do a little intro while you get set up. So yeah, Phil has been a part of the STAC community for a while, and then most recently he's been leading all the charge on the 1.0.0 of the STAC API, and recently put out the RC1 release. And then with this tutorial, he's going to dive deep into CQL2, which is kind of the biggest new feature in STAC API in the last few months. Yeah, which was probably a bigger feature than we were necessarily expecting, working with OGC on that, but super powerful. So I think he's going to give a lot of overview on what all you can do with it. So yeah, over to you, Phil.
All right, sounds good. Okay, so I'm going to be, as Chris said, I'm going to be talking some today about search using CQL2 in STAC API. And this is using the filter extension in STAC API. I'll talk a little bit about what the different elements of the STAC API are and what the extensions are. In this talk, I'm a senior geospatial software engineer at Element 84. I work with Pete, who did his lightning talk earlier about the STAC Rust tools. And as Chris said, I'm also the sort of the STAC API shepherd in getting the API polished and released. All right, so just a brief reminder of what STAC is. It's a group of composable specifications for both describing data and searching data, and it's intended so that people can use exactly the different components that they need to use without having to implement a lot of stuff that isn't relevant to their use case, and being able to put together really good sets of metadata and really good APIs that work well for their specific use cases, and extend both of those in ways that are useful to them, and possibly contribute those back to the community for other people to have those sorts of standards. So STAC is related to the OGC standards in that the STAC API extends the behavior of OGC API features, and a STAC item extends a GeoJSON feature. They add things to both while also being conformant to those specs, and that allows us a lot of flexibility to work with existing tooling and just add additional features on top of that. The main thing I'm going to be focusing on today with the CQL2 support is a specific conformance class in STAC API called item search. This adds a new endpoint /search that allows a cross-collection search within a catalog. By default, the OGC API features endpoints only search within a single catalog, although they're also working on a cross-collection mechanism now that's I think it's either in development or in draft. And STAC API is specifically thinking of like all these items in one place together, and you're searching over a lot of different items from different collections, different satellites, different everything. The core STAC API item search has a few parameters that you can search on. You've got datetime, where you can search on a single instant or an interval. You've got a bounding box that you can search spatially. Both datetime and bounding box are also supported by the OGC API features endpoints to search items on. The search endpoint additionally adds an IDs parameter that you can restrict the query if you know the exact ID of the item you're looking for, or restrict it to a single collection. Additionally adds a spatial parameter intersects that takes a GeoJSON geometry instead of just a B-box, which allows a lot more precision for searching over an area that you're interested in. the big limitation here is that stacked items provide a huge amount of metadata in their properties, but there's no way in this core item search behavior to search for it. And that was intentional because one of the principles of all of the STAC specs is that they're composable. And so it was sort of intentionally not included in the item search specification because we knew there were probably going to be a large number of different ways that people could possibly search over items using different languages, and we weren't exactly sure what the best way to that would be. So it's in another STAC API conformance class. The most common thing people want to search over is cloud cover. That's by far the most common use for this. And for simple things like that, we added the STAC API query extension, which included a proprietary JSON-based language that we sort of refer to as STACQL. It was explicit to, it's intentionally for STAC, and it's intentionally very simple. But that also means that it's not a standardized language like SQL, or as we're talking about now, CQL is. It was really just a very fast way to get some basic metadata attribute query going. And that's actually been implemented several times. I was watching Tom Osberger's presentation yesterday, and he had some query extension queries as part of his notebook queries to his STAC API in Planetary Computer, and it works fairly well. We're going to continue to support that, but the future going forward is using the filter extension, and the filter extension supports CQL2. So I'm going to start off with a little bit of explanation about what CQL2 actually is. And I'm going to start by saying what CQL2 is not. I want to make this really clear because a couple of years ago, I did an implementation of CQL2 or of CQL for a STAC API that I was working on. And I actually misunderstood which CQL we were talking about and implemented a totally different CQL support in my STAC API. So what it is not is the classic OGC CQL as defined in the general model. Although that CQL did serve as a significant influence on this CQL's CQL2 text mode. It's also not the search and retrieve via URL contextual query language, also known as the common query language, and it's not the Cassandra query language. It's the OGC common query language, and we try to be pretty consistent about calling it CQL2 now so that it's really clear exactly which query language this is. This was originally part of the OGC API features part 3, filtering and the common query language CQL specification. It was realized that CQL2 actually has more applicability to various use cases outside of just the OGC API features part 3 implementation. So it's been broken out into its own standalone specification that will then be used by part 3. But it also means that it can be used by other specifications going forward. And it's turned out to be a really, really nice language. I want to speak a little bit to the process that CQL2 went through in its development too, that we in the STAC API community were very involved with the OGC folks, Peter and Clements specifically when they were developing the CQL2 language. And it was a really great collaboration of our focusing on like very, very practical concerns about what we wanted to do queries on, and then wanting to define a very well-defined, generally applicable language to be reused within many, many different features. And we ended up going through several iterations in STAC API in different betas. And what's come out of it is really, really great language for doing these types of spatial queries. Just to give you a brief flavor of what these sort of queries look like, there's two different flavors. There's CQL2 text and CQL2 JSON. The text format looks similar to SQL. As many of these languages end up looking, and the JSON format uses a series of op and args parameters with lists of arguments to recursively construct these queries. I'll go into more of this later, but this is just an idea, just to give you an idea of like what these type of queries look like. Okay, so the STAC API Filter Extension, most of the behavior in STAC, both Core STAC and STAC API, are done through extensions. This allows a lot more decoupling of the behaviors and allows them to be versioned independently. Currently, the STAC API spec is in 1.0.0 RC1 version. We'll probably split out the filter version and version that independently because the CQL2 spec is currently still in draft. We'll probably split that out. So if any changes do occur, we can version it independently and people can implement whatever version is available at the time that they're doing their implementation. And then that gives more flexibility going forward in updating STAC API independently of the STAC API filter extension. We introduced this in beta.2, which came out, I think, a little over a year ago. And it's migrated, migrated as we've released versions and the CQL2 spec has evolved into the current form, which is thought to be very, very stable and is starting to have some implementations. Okay, I'm going to start. One of the key aspects that I keep, I've said several times, is that a lot of these specs are intended to be composable and modular, so that you can choose what to implement depending on what your use cases are, and that is both for clients and servers. That you can implement whatever behaviors you need to, you can do it in an incremental fashion, and you can advertise what you actually support through conformance classes. And likewise, clients can look at these conformance classes and know what features an API implements, and then only surface those features to the API user. Probably the three conformance classes that are part of CQL2 and therefore filter extension that are getting the most, will probably get the most use, are the basic CQL2, the advanced comparison operators, and the basic spatial operators. There's 10 classes overall, and the other 7 definitely have their uses, but they're more complex to implement. And I'll talk a little bit more about these later. Okay, so basic CQL2 conformance class has logical operators in it, so you can do and, ors, or nots. It has the basic comparison operators and an is null operator that works against all the primitive types, string, numeric, Boolean, date, and datetime within an expression. This is the example that I showed earlier. With this, I can match collection to a string. I can match cloud cover to be less than a number. Likewise, I could, if I have mixed data, some that has cloud cover and some that does not, I could say the cloud cover either has to be less than 10, but if there's no cloud cover mentioned, then I also want that. I also want that returned. That's useful for cases like Nate that doesn't have cloud cover as a value, but is in general is generally cloud free. So this is, this even if you could filter on properties within an item in the core item search, just being able to add these together and say, I want this property or this property is really, really useful. And same thing with collection. You could filter different attributes based on the collections by just ORing and ANDing them together. Likewise, most of those parameters that I showed earlier that are supported directly with the item search endpoint, like date time, those can also be pushed down into CQL2 filter expressions. And here we have an example of filtering by date time, where the date time has to be less than a timestamp with an ISO 86 or a RFC 3339 date time indicating that timestamp. Likewise, these are kind of hard to fit on a single screen because the JSON is so verbose. But here's an example of the first query we had above, where we're just saying it has to be the Sentinel-2 L2A collection, and the cloud cover has to be less than 10. And likewise, here's a couple of the other predicates that we could say. We can say that the date time has to be greater. Well, I think I said greater than here, but the date time is compared to a single timestamp. And likewise, the is null operator allows us to check that in a certain property. Okay, so those are the basic operators. The next conformance class is the advanced comparison operators, like between and in. Between and in can always be expressed by using a conjunction or a disjunction, and an or, with a series of greater than or less than comparisons. But there's no other way to express an SQL style like expression where you're doing a glob like match on a string. So here's an example of those. Between takes an argument of the property and then two values that it needs to be between. Like we'll take a property and then an expression with percent signs that express the match on either side of it. And then in we'll take a property name and a list of values that it could possibly have. And then the basic spatial operators, it's plural, but there's only one, spatial intersects. And this has the same semantics as the intersect parameter that item search has. But because the OGC API features endpoints don't already have an intersects parameter, it's important to have this as part of CQL2. It's also important because you may want to just push everything down into the filter expression and not have to mix and match the item search parameters and CQL2 expressions in that filter. You can just put them all in the filter. And this is what the spatial intersects parameter would look like. You choose the property that you're filtering on, and then a GeoJSON geometry that you want that to intersect. Yeah, and so the question is why S intersects instead of ST intersects like other common applications. I don't actually know that. That may go back to some of the other OGC specifications. And Peter says that he knows, but can't speak right now. Peter, if you want to put that in the chat, I'll read it to everyone.
Or maybe not.
Yeah, I'll just go on. Well, Peter says that they're all just a single. Just for consistency's sake, they're all just a single prefix letter. So S for spatial, T for temporal, A for array. So yeah. Then I'll just briefly talk about some of the other conformance classes. I'm not going to give examples of these, although the STAC API Filter Extension definition and the CQL2 definitions have a lot of examples for these that you can go find if you're interested. The spatial operators extension adds an additional, on top of the basic spatial operators class, adds the other DEM 9IM spatial operators that define adjoining and within and all the other spatial operators that exist. The temporal operators also define a number of different ranges of different instance and interval operations. Custom functions defines functions that you can actually use within the CQL2 expressions. These are useful if there's some transformation that the values need to go through in order to compare them properly. Arithmetic expressions in the operations, array operators, equals, contains, contained by, and overlaps. Those can be useful. I'm actually talk a little bit about one of the array operator use cases later on. And then the property to property comparisons. By default, I didn't mention this, but I sort of implied it. By default, the basic CQL2 class only allows you to compare a property on the left-hand side of the comparison and a literal value on the right-hand side of the comparison. The property to property comparisons class allows you to compare one property to another property. And that's a separate class because there are a number of data stores in which it's actually really hard to do property to property comparisons in. And so this allows a little bit easier of initial implementation. And then finally, the accent and case insensitive comparison operators for working with languages that have more than just ASCII characters in them. Okay. So I've been talking a lot about how to actually construct the queries, construct the expressions that are in the queries. But one of the biggest problems with many of these query languages is that you don't actually know what terms and property values you can use in the expressions. When we're talking about something like SQL, you can look at the table column names, or look at an out of band set of documentation that says here's all the different terms that you can use, here's all the different property names. But that's not great when you have a general purpose API that you're allowing people to do queries over and they don't know what they can actually query on. And so Queryables is this really great mechanism that explicitly defines what terms, what properties can be used in a query. So, for example, here I use collection, and I use a property called EO cloud_cover. Well, if you know STAC well, collection is usually a top level field in the item JSON, but EO cloud cover is actually in the properties object in an item, whereas I've just used it raw here. How do I know that this API isn't expecting that to be properties.EO cloud cover? And the way I do that is I can actually look at the Queryables definition. So this is a endpoint that's either at the root of a STAC API at the Queryables path, or they can also be within a collection, so that individual collections can advertise that they support a certain set of properties that can be used in CQL2 queries. And this is great because it decouples the actual stack item representation from the way that they can be queried over. And so, for example, instead of having to say properties.EO cloud_cover, I could simply say there's a queryable called cloud cover, one word, and that can be used anywhere in the property, or that can be used anywhere in the expression as a property. And then these are well defined using a JSON schema, so that there's typing information associated with that. JSON schema allows you to do even more things, like define a regex that the value has to adhere to. For example, datetime is that way. I'll show an example of that in a few minutes. But in this example here, we've said that the properties.datetime value has a name of datetime, and the cloud cover has a name of cloud_cover. We've eliminated the EO colon from it because it's unlikely that it will conflict with any other property name. And then we can just use these in our expressions. And even better, we're actually referencing the schemas, the JSON schemas that are used in the definition of these properties in STAC. Datetime, we're referencing the core item spec. For cloud cover, we're referencing the EO extension. And so we don't have to redefine them. We get really, really high quality definitions automatically. And so, as I was saying here, the queryables in that previous JSON schema definition are saying, here are the names that you can use in your CQL expressions, and here's how they map to the actual fields in the item, which is completely transparent or opaque to the user. All they know is that they're querying against these names, and then the server will translate that into an appropriate query against the data store. A really great example of this of the use of this schema is the Microsoft Planetary Computer. Through Element 84, we have done some work on the Planetary Computer, although not this. I'm mostly presenting this because I think it's a really great example of what can be done dynamically with the UI with these queryables. And this UI is from the Planetary Computer's Explore interface. It uses queryables to define all of these custom filters. The acquired filter, which is a date, cloud cover, orbit state, all these other ones. There's a list of probably 25 in in these filters that are dynamically driven based on what the Queryables endpoint says exists. So date times referencing the item's properties date time. It's in the UI, it's simply, or in the API, it's simply referencing the item spec. And then that item spec actually defines it as either string or null. It's if it's a string, it has to use the datetime format. And even more restrictive, in STAC, the pattern has to be in UTC, either with a 0 or a Z offset. So this like really allows a UI developer to provide an interface that restricts what users can actually put in for these filter mechanisms, so that they're more likely to create a valid query and create a query that actually has meaning with the data that exists and is what they intend. Same thing for cloud cover. It's referencing the EO cloud cover definition. It is a number, and it has a min and max of 0 to 100, so that a range slider can be displayed to the user to choose what cloud cover they want. Additionally, here's an example of an enum where the orbits, the satellite, I think it's called the SAT extension, or is it called this? It's either called the SAT extension or the satellite extension. Uses has a field called orbit state. This definition Queryables directly references that, and it's defined as an enum, and then that enum is populated directly into the UI, so the user can only choose the 3 options that actually have meaning in the query that they're trying to construct. So by default with this Queryables mechanism, the only valid Queryables that can be used in an expression are the ones that are defined in that schema. But there's a property called additional properties in the schema that says users can try to use other properties. They may not work, they may not have the expected behavior, but it's not going to be an immediate failure if they do try to use other properties. And this is sometimes useful for heterogeneous data sets that have that some items have certain fields and other items have other fields, and it's difficult to actually get a complete listing of all the possible fields that you might be able to query over. This is sort of an escape hatch that says, okay, you can try to do other things. They may not work, but you can try to do them. And then the software ecosystem, for this I'll talk about for a minute. We released the STAC API 1.0.0 RC1 release about 2 months ago. There were some changes to CQL2 in that, but we've been slowly having fewer and fewer changes in the betas and and now this RC as time goes on. So we've had quite a bit of implementation work that's been going on, and is rapidly catching up to RC1. As for backend support, STAC API PG-Stack supports the CQL2 JSON format via PG-Stack supporting that. GeoServer supports it via GeoTools, but only supports the CQL2 text format. PyGeoFilter supports CQL2 JSON, and the extra platform spatial library supports CQL2 text. And then several of the clients, client support in PyStack will allow you to run it with filters, but you have to explicitly say that the filter language is a CQL2 JSON, or it assumes an earlier version of the CQL spec. Here's I'll share out these slides soon, and here's some references to the various specifications and a lot of really great examples of how to use CQL2. And yeah, thanks a lot for listening, and I'll look in the chat now for some questions and start going through those. So Robin asked about this is a great point. So he asked about it points out that the Microsoft Planetary Computer queryables are basically empty, and that's true at the root level, because I think in this example here, let me open this up and look. So the currently deployed queryables in Planetary Computer, there aren't any listed at the root level, meaning, which is advertising that there are no fields that you can query the entire data set on, because each collection of each type of data, whether it's Aster, Sentinel, all have very different metadata associated with them and very different properties associated with them. So the root should basically only be something that the fields that you can query every single item in that catalog for. That's generally very small. It's usually more than none, because you should generally be able to query ID, collection, geometry, date time in any of those. So that document's probably a little shorter than it actually should be, but it's good at pointing out what the differences there. Yeah, Tim asks, has there been any discussion about including STAC queryable metadata in the existing collection summaries? And I'm not actually sure what that would look like. But it looks like there's a good discussion on that in the Gitter channel. Okay, so is there a way in CQL2 to get sorted outputs? Like, I'd like to find the top 10 images in a year with the smallest cloud cover. Yeah, so that wouldn't actually be part of CQL2. That's part of the sort extension, as David points out. The sort extension would allow you to sort by cloud cover, although the existing sort extension suffers from the problem that there's no way to advertise what things you can actually sort over. So that's a possible future extension to that. I know OGC is working on that with their sortable work too. These UBLs are really, they add a lot to implementation and add a lot of work to the spec work and the implementation work, but they provide such a great API-driven client interface that they're very worth it.
Hey Phil, I think I can talk now, right?
Oh yeah.
Great. Yes. So in what's happening in OGC with sortables is we adopted the sort of syntax that STAC had for specifying sortables, and we added a sortables endpoint for exactly the reason that you just said. They're very good for API-driven development. So the OGC definition will have a sortables, which is just another type of schema. So in OGC, we have a bunch of different types of schemas. So you have the presentable, or just the regular schema that you get when you do a query. You have the queryable schema, which is the sub-schema that you can use for querying. You have the sortable schema, which is the sub-schema that you can use for sorting. And the other thing I'd like to point out is that you could also put synthetic properties into these schemas, right? They don't have to necessarily map to some property that's in your data store. If your server knows how to handle the synthetic property, that's perfectly reasonable and legal as well. Thanks.
Oh yeah, thanks, Peter. That was one thing that I had meant to bring up. I said I was going to bring it up, and then I forgot to. The decoupling of the advertised queryable from the actual structure of the item means that you can, as Peter said, use synthetic, I guess what we call synthetic queryable, which are queryable that where there's no like direct correlation to a property in the item. And so one of the examples that I use for this is in an item, assets can have the EO bands extension, which define the name of the bands that are in that asset. So you could say like, you know, this asset has a red band, a blue band, and a green band, or you know, this asset has this type, this collection of bands in it. And there's no easy way to search on that because it's actually a list of things, and they're all in different objects, really. So you could advertise that there is a queryable called bands, and it's just the list of all the bands sort of added to a single, as if they were added to a single array. And then a user could use the arrays extension to search that the band that they were interested was in this synthesized queryable called bands that doesn't actually exist in the item. And then the server would rewrite that in a way that made sense to query the data store with. And so those are really powerful because you can expose an easy way for a user to query data that's in a bunch of different places in your item. Matthias asked, have there been any thoughts to serve queryables with the refs resolved? If you'd like to request queryables from Stack Browser, it seems slow to have to retrieve all of them. Yeah, I think that's actually a really good point. I think in defining them, you would probably use the references, but then there's, you know, there's tools out there that will resolve all the refs and then give you a resolved JSON schema back. And I think that's probably in implementation, what you'd want to do is reference them in your definition of them, but then generate a version that actually has all of them resolved. So there's no, you don't have to do, the client doesn't have to do multiple queries to retrieve however many stack JSON specs they need to. David Bittner said that PGStack also supports CQL2 text via converting to CQL2 JSON with PyGeoFilter. I had forgotten about that because that's a really good implementation point, that if you can support one of them, there's conversion tools to convert to the other. And so implementing CQL2 JSON means that you can easily also support CQL2 text via the PyGeoFilter, or if there are any that exist for other languages.
Yeah, just to circle back to Matthias's question quickly, Phil, if I can. Generally, servers, when they generate the queryables, they actually, you know, resolve any kinds of references like that so that you get a full JSON schema. And one of the reasons to do that is that some servers will generate a runtime list of enumerations for the properties, so that when you're building your query, you actually have a good chance of constructing a predicate that will actually return something, as opposed to guessing what values might exist for, you know, whatever property. So they dynamically, you know, include the enumeration list, and it's built up at runtime sort of thing. So it queries the database and says, oh, okay, property 1 has these 5 values right now. So if you use any one of them and you do a query predicate, you have a good chance of actually finding something.
Okay, so there's apparently a CQL2 parser in Go that I hadn't heard of. That's good to know of. PG feature serve. Okay. Are there any other questions or things of interest? I could run some queries if that's of interest. They're not terribly interesting, but let's see. Let me get this out of this. Let's see, there we go. Yeah, so Planetary Computer is the implementation right now that has the or public deployment that has the best support right now for CQL2. Here I'm going to run this this query. So this is restricting the collection to Sentinel-2 L2A collection, and then cloud cover is less than 10%. And then I'm also using the fields extension, which allows you to restrict the results so that I don't get nearly as much data back, and I can easily see my cloud cover values. You know, one thing that I think is interesting about this is that the CQL2 JSON format is nice because it's basically already it's effectively already a parsed tree of the elements in the query, but it's extremely hard to write because it's a lot of JSON to get correct. But in general, people won't be writing these queries directly. They'll be using some sort of other tool, like whether most people will be using a UI that has drop-down menus in it. And you know, as we saw earlier, the Queryables allow those UIs to be constructed in a way that is really, really relevant to what is actually happening, and it's not just a free-form query. It's, you know, very restricted in what the UI elements can be. Yeah, so so Matthias points out that I can query globally for EO Cloud Cover, but it's not listed in the queryables. And I think this is a sort of an artifact of the fact that this implementation in Planetary Computer is still ongoing, and you know, we only recently came out with the final version of or not the final version, the RC1 of the filter extension, and that things haven't quite caught up with you know, what can actually be done in that implementation. One of the things that I did notice was, well, if you look in the Planetary Computer Explorer interface, the options change depending on which collection you've chosen, and so the filter options are being driven off of that collection's queryables rather than the global queryables. Even though, as I demonstrated here, I can actually search for properties that don't exist in the queryables right now. All right. Well, thanks everyone for listening, and yeah, so Alex says, are there implementations to simplify building CQL statements in code, Jupyter Notebooks, or does PyStack abstract it? Right now, I think PyStack doesn't have any specific abstractions for CQL2. It's just a JSON blob, but I think that that's something that will be, you know, will be added over time, so that those can be constructed in a more programmatic way rather than just building a, you know, sort of an arbitrary dict that hopefully is, you know, conforms to the schema. But you know, there's a lot of like builder patterns and things like that that exist for SQL and apply pretty well to CQL2 also. we're at a really exciting time right now because we've just gotten these specifications sort of ironed out, and now the implementations are going forward. And so if people are interested in getting involved with some of the implementations, they're definitely ongoing and need coding and testing and just even your use cases are really valuable to know what you're trying to query and what needs to be implemented to support those types of queries easily, particularly with like data scientist usage in Jupyter notebooks.
Yeah, and following on that, we've got a little bit of funding from the STAC fundraising efforts in the past to help support some of those implementations. It's not much money, but if you happen to be working on an implementation, and like our thought is give a bit of money to try to get that sooner so we can get feedback on the spec itself. And I think that's what's going to really put us from RC1 to 1.0.0 is when we see a number of different implementations and feel really solid about everyone working with it. So cool. Thanks, Phil. This was super great.
Thanks.
And we got a few minutes to the next session, but I think we'll probably just pause, people in chat on the Gitter if you would like, and then looks like we got many of the presenters on, so I'll be back in 5 or 6 or 7 minutes and we'll kick that session off. Thanks, Phil.
Thanks, Chris.